Okay, everyone. I'm super excited that we're trying this flipped classroom. So we're going to be doing our lecture on topic 2.5, which is Lewis diagrams. So take a moment, turn to page 26, pause the video as you need to. You can speed it up and slow it down, and pause and go back and all that great stuff. Now, this is our big goal for today. By the end of this lecture, if I give you a formula like pH3, I would want to see that you were able to draw the Lewis dot structure of that molecule. Okay, and a lot of this does hinge on this idea of the octet rule. And I'm going to show you a different way of going about this, and know that the octet rule is a guideline, and it's a guideline that works really well, but there are definitely occasions where the octet rule is not followed, and we do result in a more stable atom. Okay, so what is the octet rule? It's this idea that atoms, if they feel like they have 8 valence electrons, then that's really similar to noble gases, and what we know about noble gases is that they don't react, that they're relatively stable. So let me give you an example of this. First off, a reminder, if you see a molecule and it has a line, that this line represents a bond, and that bond has 1 electron being shared by each atom. So if this was a hydrogen and a hydrogen, like each hydrogen is reluctantly sharing 1 valence electrons. But because they get into this tug of war, they both feel like, instead of having 1, they kind of both feel like they have 2 valence electrons. This one kind of feels like it has 2, and that one kind of feels like it has 2, instead of having just 1 apiece. And a reminder, because this is going to show up quite a bit. Any element in group 1 has 1 valence electron, and group 2 we have 2 valence electrons. We're going to skip our transition metals and look at 13. That would be 3 valence electrons. 14 is 4 valence electrons. 15 is 5 valence electrons. 16 is 6 valence electrons. Anything in group 17 is 7 valence electrons, and then we got 8 valence electrons for group 18, and there's our noble gases. And like we said, noble gases are stable, and so it bears to reason that if other atoms also had 8 valence electrons, they might find that same level of stability. Okay, so octet rule, becoming stable. Becoming stable when an atom has 8 valence electrons. An atom has 8 valence electrons. Okay, now one difference between the videos and lecture time in class is I'm not gonna be talking as slowly, because I know that you're able to rewind if you need to, and I'm not gonna be repeating statements too often. So if you need to pause so you can write down notes, please do that. So becoming stable when an atom has 8 valence electrons. Okay. Other thing about the octet rule, if I have an atom such as sodium, and sodium is in group 1, so it has 1 valence electron. So these Lewis dot structures, the dots that are not bonded, they are representing 1 valence electron. Okay, and then another example would be like neon. Neon has 8 valence electrons. And so we'd see something like that. But what if sodium becomes an ion? What if sodium loses that valence electron? And so then it looks like this. But guess what? Sodium had 11 electrons total, where neon has 10 electrons total. And so what if this becomes a sodium with a +1 charge, where it lost an electron? Now it's the same as neon. So whether it has 8 dots around it or no dots around it, those are both stable, like 8 valence electron structures. An exception is hydrogen. Hydrogen is really stable like this, so instead of wanting 8, it tends to want a duet instead of an octet. And so we have hydrogen, little exception here, only wanting 2 valence electrons instead of 8. Okay. Reminder, ionic compounds happen between metals and nonmetals, and they lose electrons and gain electrons. So like, what if I want to do the Lewis dot structure for magnesium chloride? So I have magnesium here, and let's find magnesium. Oh, magnesium has 2 valence electrons because it's in group 2. And chlorine. Here's our metal, and let's do a nonmetal, which is chlorine. And chlorine is in group 17, so it has 7 valence electrons. Okay, there's my 7. Now, metals lose electrons and nonmetals gain electrons. So magnesium is going to lose this electron, and chlorine's going to gain that electron. That's great. Now chlorine has 8, but wait, magnesium wants to get to a place that it has none, right? And so what if another chlorine atom comes in? And remember, neutral chlorine has 7 valence electrons. And so if this magnesium loses the other electron to a second chlorine, now it feels like it's lost both its valence electrons and it gets to that stable structure. So the result here would be a magnesium, and I'm going to get rid of those dots, and we get a 2+, and then we have chlorine that instead of 7 valence electrons, now it's got 8 valence electrons. When something turns into an ion, this includes atoms and molecules, we put it in brackets, and then we put the charge on the outside. And it gained 1, so that's why it became a negative. But there was 2 chlorines that this happened to. Okay, 2 chlorines that this happened to. And so we get a minus there. And remember how negative anions and positive cations, there's electrostatic attraction. Those are the ionic bonds. And so the result is a structure that's MgCl2, because there was 1 magnesium and 2 chlorines. Or we could crisscross, right? MgCl, we got a 2+ and a minus, and so you can crisscross to get that same MgCl2. But the octet rule is still working there. Okay. For covalent things, instead of gaining and losing, now it's going to be sharing. Yes, reluctantly sharing, tug of war, but the same still holds true. So what if we have a water molecule? Okay, so oxygen's going to go in the middle, and it has 2 lone pairs. Okay, that's a lone pair. It's 2 electrons that oxygen has, but they're not bonded electrons, right? They're not part of the bonding electrons. And then we have hydrogen and we have hydrogen. Okay? So this hydrogen is sharing 1 electron, but because oxygen is sharing 1, it feels like it has 2 valence electrons. And this same with this hydrogen, it feels like it has 2 valence electrons. And now here's what's really cool, is this oxygen. This oxygen feels like it has 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons. 2 valence electrons, 2 valence electrons. This is a really structurally sound and low energy stable molecule because we have that duet for hydrogen. it has 2 valence electrons, and we have the octet for the oxygen in the middle. And so then it also stabilizes. Another hint to help us with these in the future, nature tends towards symmetry. So you can kind of see how our hydrogens are on opposite sides from each other, because we do tend to get symmetry out in nature. Okay. Now, I'm going to give you our shorthand way of doing this. And then I'm going to show you the old way that we learned back in Honors Chem and Gen Chem. So the first thing, here's how Mrs. H's way of doing Lewis dot structures. Okay? I know nature's going to tend towards symmetry, so I'm going to put phosphorus in the middle here. And then phosphorus has, let's see, 5 valence electrons. So I'm looking at this. Here's my phosphorus, and I have 5 valence electrons, right? 1, 2, 3, 4, 5, okay? There is hydrogen, and remember, hydrogens have 1 valence electrons, but our goal is to get to an octet. And so what if we do a hydrogen here, because then this can share. Right? And we do a hydrogen here, and then those are sharing, and then we have a hydrogen here, and so then those are sharing. Okay? So we've stumbled onto the same idea that hydrogen wants to have 2, and that one hydrogen feels like it has 2, and that hydrogen feels like it has 2, and phosphorus, even though it brought 5 in, it is sharing, so now it feels like it has 2, 4, 6, 8. So we're obeying that octet rule, and we get this really stable molecule. Okay? This would be, let's see, what's the best way of describing it? Oh, another way of writing this, that's what I wanted to show you. Instead of putting both the dots, we often just draw the line. So just a heads up on that. Like, we often do not include the dots on these bonded electrons, and I just need you to recognize that. Oh, look, I'm even going to flip it around. There's another valid molecule of pH3. Okay. The phosphorus feels like it has 2, 4, 6, 8, and the hydrogens feel like they each have 2. Okay, so that's like Mrs. H's quicker way of doing this, and it also works with suboctets and expanded octets, and I'll show you that in just a moment. The way that we learned back in Gen Chem and Honors Chem is we followed the list of steps, and the first step was counting our valence electrons. Okay. Count valence electrons. The second step was decide what's going to go in the middle. Like decide which atom's going to go in the middle or the center. And then we started with single bonds to remaining atoms. Okay, single bonds to our remaining atoms. And then we completed the octet for outside atoms. Not the center, the outside atoms. Sometimes this is a duet if it's hydrogen. So complete the octet for outside atoms, but if it's hydrogen, I'd be like completing the duet for outside atoms. And then, so the last thing would be, or second to last, put any remaining electrons as pairs on the center. So if we have any remaining electrons, we're going to put them as pairs on the center. And then the last step is double or triple bonds if needed. So, step 1, count valence electrons. I have 2 hydrogens and 1 sulfur. So each of those hydrogens are in group 1, so they have 1 valence electron. Sulfur is in group 16, so it has 6 valence electrons. So I have 1 valence plus 1 valence plus 6 valence. Each of the hydrogens plus the sulfur, so we get 8 valence electrons. Now, nature tends towards symmetry, and because of that, I'm going to put sulfur in the middle. Then I'm going to do single bonds to the remaining atoms, and what's remaining is 2 hydrogens. So I'm going to do single bonds to the other hydrogens. Now we need to complete the octet for the outside atoms. The hydrogens are the outsides. So remember, they just want a duet, and yep, hydrogen feels like it has 2, and hydrogen feels like it has 2, so I don't need to do anything there. All the remaining electrons we're going to put as pairs on the center. There are 8 valence electrons, and we've used 2, 4 of the 8. So I'm going to put the remaining 4 as pairs on the center. Now, I don't need to do double or triple bonds because it's not needed. The hydrogens feel like they have a duet, and the sulfur feels like it has an octet, 2, 4, 6, 8. So that one's done. Okay. HCl. Pause the video and try this, and then check back in. There's my Lewis dot structure. Remember that chlorine had 7 valence electrons, so 1, 2, 3, 4, 5, 6, 7. There's its 7th right there, and hydrogen only had 1. But by having them share in this way, hydrogen now feels like it has 2 valence electrons, or a duet, and the chlorine now feels like it has 2, 4, 6, 8. Okay. Sigma and pi bonds. Man, doesn't this have a different meaning now? Years ago, like when I first taught sigma and pi, it was not the same as it is today. If we have a single bond, or a double bond, or a triple bond. Okay, a single bond, another name for a single bond is a sigma bond. So this would be 1 sigma bond. And this is true for the double and the triple. There's 2 bonds in a double. One of the 2, and it doesn't really matter which one, but one of them is a sigma bond. Same for the triple bond. One of the 3 bonds here we would call a sigma bond. For a double bond, one of them is already the sigma, the other one is a pi bond. So we have 1 sigma bond, 1 pi bond. Where with a triple bond, this would be 1 sigma bond and 2 pi bonds. Okay? So this molecule just has 1 sigma bond. This molecule has 2 sigma bonds. And this one here has 1, 2, 3 sigma bonds. That's a common question on AP Chem, by the way, is you like draw a Lewis dot structure, and then it'll ask you how many sigma and how many pi bonds. Alrighty, so this is what we're going to do. We're going to do one of these together, and then at the beginning of next class, we'll do a couple more to warm up. Notice that there's hydrogens here and there's a hydrogen there. There's a reason why they separated it. It's telling us that this carbon is bonded to these hydrogens, and it's telling us that this oxygen is bonded to that hydrogen. Another little tip or trick is that carbons tend to be in the center, and if you have more than one carbon, they form a chain. So I'm going to put carbon in the middle right now, and carbon has 4 valence electrons. 1, 2, 3, 4. Okay, and we're going to be bonded to 3 hydrogens there. But that leaves one here because it's going to bond to the oxygen. So I'm going to start by bonding to this oxygen. Now, reminder, oxygen has 6 valence electrons because it's in group 16. And right now I'm just showing 1. So what if I have 2 more right here? So this would be 1, 2, 3, 4, 5, and that would leave a leftover 1, 4, 6. And it's going to be bonded to the hydrogen there. Okay, now this structure is so cool because notice all the hydrogens have duets. And this carbon now feels like it has 2, 4, 6, 8. And this oxygen feels like it has 2, 4, 6, 8. Okay. Okay. I'm going to save. Let me double check. Yeah. I'm going to save ions for class time. So we're going to do those 2 at the beginning of class. We're just going to be adding and taking away electrons. So NO3 plus 1 extra electron, or NH4 but removing an electron. So more on that at the beginning of next class. Okay. We're going to end this lecture by talking about suboctets and expanded octets. Suboctets mean sub or less than 8, where expanded octets mean more than 8. Okay? So here's one that I see quite a bit. What if I want to do the Lewis dot structure for this like boron trifluoride? Okay? I know that nature tends towards symmetry, so I'm going to put boron in the middle here, and our fluorines are going to be on the outside. Okay. Something I've noticed as I've been doing Lewis dot structures for years and years, and this goes right along with formal charge, which we'll learn about next time, that the octet rule doesn't seem to be quite as influential as looking at the amount of valence electrons and not exceeding that, okay? Meaning, like, boron is in group 13, so I know it has 3 valence electrons here. And this is convenient because I have 3 fluorines that are wanting to be bonded to that. And so there's a fluorine, there's a fluorine, and there's a fluorine. Okay. Each of those fluorines have 7 valence electrons, and they just shared 1 of those 7. So there's 1 of the 7. And notice there's the remaining 7. 1, 2, 3, 4, 5, 6, 7. And then this fluorine, same thing. Like that. The fluorines are happy. The fluorines each have an octet, 2, 4, 6, 8, 2, 4, 6, 8, but the center does not have an octet, 2, 4, 6. Now, theoretically, could we take one of those lone pairs and turn it into a bonded pair? And maybe I'll grab one from here. I'll take that and I'll put it right there. Now, normally we would go like, oh, isn't this better? Because now boron has an octet and it didn't have an octet before. 2, 4, 6, 8, 2, 4, oh, sorry, erase that because I moved it to be a bonded pair. 2, 4, 6, 8, like everything has an octet, but it turns out that this does not occur in nature. Boron started with 3 valence electrons, and it's sharing those 3. Like, it didn't have 4, right? It didn't have 4 that it could share. And so this is actually a more stable structure than that one is. Okay. Oh, by the way, the ones that tend to form suboctets are beryllium, boron, and aluminum. Those are our main, like, central suboctet items. Beryllium only has 2 valence electrons, so it tends to go like that with things on the outside. We see what boron looks like, and aluminum is also in the middle with boron, and so it does something similar. Okay. Expanded octets. Expanded octets can occur. They don't have to occur, but they can occur for nonmetals that are in period 3, so 1, 2, 3, and lower. So 1, 2, 3. These ones here, these can have an expanded octet. Okay, so let's do an example. PCl5. So first thing I noticed, I'm gonna put phosphorus in the middle, okay, and then I'm gonna show that there's 5 chlorines bonded to that. 1, 2, 3, 4, 5. Chlorine, 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 and chlorine. Okay. Chlorines have 7 valence electrons, and so it's already sharing 1, and so then here's the remainder of those. Okay, this is Mrs. H shorthand. I do not want you to do this on the AP Chem test, but I will let you do this on the homework and during class time. That is the same as that. Okay, so that's just my shorthand for showing all of those electrons. Boop, boop, boop. Okay, great. But how many electrons does phosphorus even have to share? Well, let's check. Oh, here's phosphorus. It's in group 15, so it has 5 valence electrons. And check this out. 1, 2, 3, 4, 5. So it's sharing those 5. And so this is a valid structure, and it does occur in nature. Everything has its octet on the outside, and yes, phosphorus does have more than an octet. It feels like it has 2, 4, 6, 8, 10, but it did have the 5 available to share, and that does seem to be what occurs in nature. So let me show you a tricky one. We're going to go on the next page. Let's see. Sulfur 6, yeah. Okay, we're going to go to this page, and it says AP concept checks. Please be so kind as to draw the Lewis structure for sulfur tetrafluoride. So this is a sulfur and a fluorine, and we know there's 4 of them. Okay, so nature tends towards symmetry, and this is just my quicker way of doing this. So nature tends towards symmetry, so I'm going to put sulfur in the middle, and I know that it's bonded to 4 fluorines, so I'm going to go 1, 2, 3, 4. 4 fluorines. Okay. Fluorines have 7 valence electrons, and they're sharing 1 of them, and so we get the rest of those valence electrons. So there's its 7, right? 2, 4, 6, and there's the 7 right there. So that's going to be the case for all of those. And then I'm going to ask myself, what about sulfur though? Am I accounting for all of its valence electrons? Sulfur is in group 16, so it has 6 valence electrons to share. It doesn't mean it's going to share all 6, but it does have 6, and we've used only 1, 2, 3, 4. We've only used 4 of the 6. Put remaining electrons as pairs on the center. I don't care where you put them, but let's keep them as a pair, and I'm just going to put that on the center. That is an expanded octet. This sulfur feels like it has 2, 4, 6, 8, 10 electrons. But that's okay because it had 6 valence electrons to begin with, and that's what we're still looking at now. It's sharing 4 of them, And then 2 of them, it's not sharing. It's keeping them as a pair for itself. So that is the valid Lewis dot structure for sulfur tetrafluoride. Okay, that wraps up lecture. We have ones that we've left blank that we will do together before we dive into the problem set next class. So good work, and I'm excited to see how our flipped classroom goes.